Okay, good morning. It's about 5 to 9. I'm just doing a sound and video check for this morning's lecture. If someone can give me a thumbs up on the questions lectures channel in Discord to let me know that everything's good. Excellent. Wonderful. Couple of messages coming through there on the channel, so that's wonderful. Thank you for both there. So I'll go offline for 10 minutes and we'll start the lecture at 9:05, just in case anyone's got any commitments that mean they have to get here from an earlier lecture or a tutorial. I'll see you in 10 minutes. Thank you. Okay, good morning again. It's 9:05. We'll kick off with the lecture now. Can someone just give me an indication, one more indication in the questions lectures channel that you can see the title screen and hear my audio? Okay. Wonderful. Thank you. Thank you, Harley. Let's get underway. Thanks very much. Okay, so I think I mentioned when last we spoke, which was just before the break, that we would really picked up just about all the Python language that we'd needed to start solving some problems. Sarah's lecture content last week focused on the very last little piece of the Python language, that the new part of the language that we need, and that was in the form of two-dimensional arrays. And Sarah also looked at the utilization of those arrays for doing some image processing. So looking at being able to display images, and then also the behind the scenes work with working with arrays. And the lab questions this week are all around giving you the opportunity to exercise some of that information that Sarah presented last week. So this week's content is around solving certain types of mathematical problems, or problems that arise in engineering that need mathematics, for which the Python programming language provides support. And I've broken it into two pieces. Today's lecture, we're going to focus on something called nonlinear algebraic equations, and I'll explain what that means and show you what they look like in just a moment. And on Thursday, we'll look at a technique known as integration. I'm conscious that not all of you have studied calculus before, and so the lecture content this week is structured around giving you the tools that you need to solve interesting engineering relevant problems, regardless of what branch of engineering you're studying, but to do that without necessarily having knowledge of calculus. Along the way, there will be some touch points around calculus that I'll point out, because all of you will be studying, or almost all of you will be studying calculus at some point in your program shortly, if not already. And so I'll point out the linkages between the content where it touches on calculus without actually requiring. So today's lecture is going to look at what are called nonlinear algebraic equations. And I'll explain exactly what that means on the following slide. So the lecture content for today is structured into 4 chunks that you can see there on page 2. I'll talk about what it means to be a nonlinear algebraic equation. Sounds a bit scary. I'll show you that it's not scary, and I'll show you what they look like. And in particular, I'll introduce a particular problem that is a simple form of nonlinear algebraic equation. And the idea is that by showing you the application of certain solution techniques for that particular problem, we can extend it to more complicated, more interesting problems down the track. And so after we set up these nonlinear algebraic equations, we'll then set about just give me a moment. I can see you can't see the slides. Sorry about that. Don't know why that's the case. Let me just give me a moment. My apologies. Apologies for that. How about that? I'm just going to pause for a moment and let you know, let you tell me if you can see the lecture slides. Wonderful. Thanks very much. Okay. Thanks for pointing that out. Thank you. Good. Okay. So you haven't missed anything. I've been telling the story. We've got the lecture overview. You can see on the slide in front of you that the lecture is structured into 4 chunks. The first one, we're going to introduce these nonlinear algebraic equations, and then we're going to set about solving those equations. I'll introduce two methods. Actually, we'll introduce three methods, but we'll focus on two of them in particular. Methods known as the bisection method and the secant method. In doing that, we'll touch on something known as Newton's method, which is very closely related to the secant method. And then we'll look at some extensions. One of those extensions will involve something that gives you the ability to time code that you've written in Python. So the timing content that we look at today is not specifically tied to solving these nonlinear algebraic equations. It's a very general technique. And if you're interested in writing large programs with large data sets and you're interested in refining your algorithms and your code, it's important to be able to know how long it takes a particular chunk of code to run. And so I'll show you how to do that too. There's different ways of doing it. I'll show you what I think is the simplest way. So let me just check on, excellent. Can't see full screen though. Okay, good now. Okay, I'll assume we're all good. Let me know in questions lectures channel if something's gone awry. Okay, let's talk about what these nonlinear algebraic equations are. The word algebraic here is I'm probably going to drop as for the most part. There are different types of equations that come up in solving engineering problems. The word algebraic here refers to the fact that there's algebra involved. There are different types of equations, and I'd rather defer what I mean by an algebraic equation until we see some other types of equations later in the course, maybe. So let's just worry about the nonlinear equations. So a nonlinear equation is something, surprisingly, that is not linear. So let me say what a linear equation is. A linear equation is the equation of a straight line. So you will have remembered from your high school mathematics that the equation of a straight line looks something like ax plus b is equal to 0. Now, you might have seen it at high school and elsewhere written in the form y equals mx plus b, where m is the gradient and b is the intercept. Ax plus b is equal to 0 and y equals mx plus b are really the same equation, just written in different form. And linear equations are super useful in engineering. They're useful because in their own right, because many phenomena that are observed in engineering applications are linear or close to linear. And the nice thing about linear equations is that they can be solved exactly. So if I give you the equation of a straight line, ax plus b is equal to 0, I can ask you for what the solution of that equation is. And the solution of the equation corresponds to the point at which the line intersects the x-axis. And the solution is given by x equals minus b on a, where a and b are numbers that define the gradient and the intercept of the straight line. Now, there are extensions of that simple linear equation form that involve systems of linear equations, and we'll probably look at those later in the course. Today, I'm just interested in linear equations in one variable x. So nonlinear equations are all the equations that can be written that don't fall into that pattern of ax plus b is equal to 0. And so most problems are actually nonlinear. So linear ones are the exception. They're the ones we can solve most easily, and they have many engineering applications. But nonlinear equations really are what drives a lot of the observed physical phenomena that we want to model and control and manage in engineering applications. Now, nonlinear equations also come in many different forms. The simplest nonlinear equation that you may have seen at high school is quadratic equations, otherwise known as parabolas, where you've got an equation that takes the form ax squared plus bx plus c is equal to 0. So that's the equation of a parabola, and the numbers a, b, and c define the shape of that parabola, its orientation, its steepness, and its intercept with the axes. And you can solve that equation if you know the numbers a, b, and c. You can solve for the two values of x that solve that quadratic equation. And that's good. You would have seen applications of that equation in high school mathematics and beyond. Now you can take that pattern of the ax squared plus bx plus c and take it to order 3. So maybe ax cubed plus bx squared plus cx plus d is equal to 0. That's known as a cubic equation of order 3. You can have quartic equations that involve the power of x being x to the 4 and so on. Now the solutions of those equations, if you know what a, b, c, d, e are, the solutions of those equations can be written out, but they're really complicated. And it's very rare that you would actually invoke those solutions to solve problems like that. If you go to higher orders, 5th order and above, trying to capture even more interesting, nonlinear, realistic behavior in the real world, you get to order 5 equations. And there's something really interesting happens. Exact solutions in many cases, in the general case, don't exist. Not that just they can't be found, but the exact solutions don't exist. Proving that actually needs some very serious mathematics that any of you that are studying 2nd and 3rd year mathematics will probably touch on. Not relevant to us here. The reason is that most equations in engineering applications have no exact pen and paper solutions. And by a pen and paper solution, I mean a form that looks like this, the solution of the quadratic equation here. X is equal to minus b plus or minus square root of b squared minus 4ac on 2a. That's what I call a pen and paper solution. On the one hand, that sounds bad because most engineering phenomena in all branches of engineering involve complicated nonlinear equations. And I've just said that no exact pen and paper solutions exist. So that sounds like it's bad news. Actually, it's not bad news at all, because while exact solutions don't exist, we can find approximate solutions. And that's one of the classic themes of engineering, which is to find an approximate solution rather than an exact solution. Approximate means, in this context, usually means as accurate as we need it to be. So this is where we draw a distinction between mathematics for its own sake and mathematics for solving engineering problems. And there's a lovely quote here by a statistician by the name of John Tukey that says it's much better to get an approximate answer to the right question than an exact answer to the wrong question. And that's absolutely a theme of mine and of engineering in general. So the general problem we're interested in solving in this lecture is in an expression that looks like fx equals 0, where fx is some formula involving x. Now the formulas that were written on page 3 here are quadratic formulas or linear formulas, and I discussed cubic, quartic, quintic, meaning orders 3, 4, and 5, and so on. But the formula for f of f for f can be really complicated. Here's a simple example of a slightly complicated formula involving x. It's this one towards the bottom of the screen. F of x is equal to either the minus x times sine of x minus cos of x. That's the type of equation that we're going to be interested in solving in today's lecture. So what do I mean by a solution? What does it mean to find a solution to f of x is equal to 0 when when f of x takes this form, either the minus x times sine x minus cos x? What does it mean? It means finding a value such as this one here, x is equal to 7.85359 and so on. That x is equal to 7.85 ... is a solution of that equation, f of x is 0, because if we substitute that value of x into this equation, if we take this value of x and substitute it into that equation, we get 0. So you can see here I've written the solutions written out to 8 decimal places. And if we substitute that value of x into the equation, x is equal to e to the minus, f is equal to e to the minus x times sine of x minus cos of x, we get 0. That's what it means to find a solution. Now, there's all sorts of interesting problems that exist that we need to consider. Do any solutions exist? Maybe not, depending on the formula for x. Maybe no solutions exist. Maybe multiple solutions exist. Maybe there are different values of x that equally satisfy that equation. We won't consider all those issues today, but I will give you a method for solving that equation and many others. And I'll give you Python code to solve that problem today. In fact, I've already posted it in Blackboard and in the lecture code channel this morning. Well, that's all very interesting. Taking an F that looks like that, I've just pulled that one out of the air. What about an engineering problem? And here's one I'm going to choose and I'm going to use throughout today's lecture. It's the problem of computing the fluid level in what's called a truncated cone. The simplest way of visualizing a truncated cone is to imagine a measuring cup, which has got angled sides, a fluid in it up to a certain level, and on the base of the measuring cup is a flat surface. So that's what a truncated cone looks like. Would be a device which shrinks to a point. A truncated cone means it's got a flat bottom. On the right hand side of slide 5, you can see a cross section of representation of that truncated cone. So it's a vessel that has a diameter of 7.5 centimeters across the circular cross section at the bottom of the vessel, 11 centimeters at the top, and a fluid level that's somewhere between 0 and the height of the vessel, which is also 11 centimeters. Now, while I've written it in terms of a measuring cup, it's got many applications in engineering settings, such as capturing the water in a dam, which might have a circular profile and a truncated cone shape, or coal or some other ore, iron ore, in a conical hopper, which is again truncated at the bottom to let the coal flow out. And so I've expressed it here in terms of a measuring cup, but it does have engineering applications. The problem we're going to be interested in solving is, for a given volume of fluid in the cup, what's the height? And you can see, if you look at the gradations on the side of the measuring cup, if you've ever looked very closely at them, you'll see that they're not equally spaced. The spacings at the bottom are larger than the spacings closer to the top. And that's constrained by the physics of the problem, because the width of the vessel is higher at the top, and so you need less of a slice to hold a particular volume of fluid than down the bottom of the hopper, where the cross section is smaller, and therefore the height of a slice needs to be higher to contain the same volume. And so the fluid level V on the vertical axis depends on the depth L. Remember, the L is the height of the fluid in the vessel, and the volume V depends on the depth L as follows: V is equal to 0.0268 L cubed plus 1.88 for L squared plus 44.15 L. I'm presenting this equation here without proof. There's a couple of ways of proving this formula. On the very last slide of today's lectures, I've given you a link that shows you a way to compute that volume. It needs a little bit of calculus. If you're studying calculus in Math 111 and Math 1110, for example, you'll have enough calculus to be able to derive that expression. For today's lecture, all I care about is that equation's been given to us. And notice how it's nonlinear. It shows up as nonlinear in a couple of ways. One of which is the dependence of V on L depends not just on L itself, but on the power of L to the power 2 and also L to the power 3. So the fact that it's not just a linear term, it's got this quadratic and cubic term, means that there's a nonlinear problem involving a nonlinear relationship between the depth of the liquid L and the volume V. It also shows up as a nonlinear problem because if we literally plot what V looks like as a function of L, the curve that results is not an exact straight line. It's pretty close to a straight line, so this is not a particularly nonlinear problem, but it's still nonlinear. The volume V is in milliliters and the height L is in centimeters. So that's what these numbers, again, the proof on the very last, the proof available at the link on the final slide shows you how to derive these numbers. I'm just giving them to you here as a problem to work with. So we need to know what the units are, V's in milliliters and L's in centimeters. So the form of that equation says if we know what L is, we can compute what V is. So if, for example, let's choose one here. If L is 2 centimeters, so there's 2 centimeters of liquid in the bottom of the measuring cup, then we can read up to the value of V, and it's about 100. Not exactly 100, but if we zoomed in, it's not quite 100, but it's pretty close to 100. So that's one way we can use that equation. If we know what the height is, what's the volume? But that's not the problem we're interested in solving today. We're interested in solving the opposite problem. Namely, if we're given the amount of volume, in this case, I'm going to choose the value 500 mils, half a litre. The question is, what's the value of L corresponding to that volume? Now you can see in the graph here that if we take the volume V is equal to 500, we read across at the level of 500, and we see it's a value that's just above this tick mark here, which is just a bit more than 8. So approximately, if there's half a litre of fluid in that measuring cup, then the height of the fluid is a bit more than 8 centimeters. But a bit more is not accurate enough for us. We want it to 2 or 3 or 4 decimal places today. In fact, we're going to compute it to about 5 or 6 decimal places. So in order to solve that problem, we need to solve the equation. On the left-hand side, the 500 corresponds to the volume of interest. And on the right-hand side is this nonlinear expression involving L, which computes the volume. And so if we match the two and then reorganize the equation so that we've got the equation in the form FL equals something is set to 0, we can solve the problem. That's the problem of interest. So this expression at the bottom of the page, the one I'm highlighting, the one that's highlighted in dark blue there now, we want to know the value of L that makes that expression equals 0. Now, if you're listening really carefully at the start of the lecture, I actually said it's possible to write the solution down to cubic equations, but it's also messy, and I'm not going to use that method here. What I'm going to do is use this equation that you see highlighted in blue on page 7. I'm going to solve it using a couple of different numerical techniques. And those techniques, yes, we could avoid the need for those techniques by using the closed form pen and paper solution to the cubic equation. But if the equation was tweaked a little bit, the likelihood is that closed form, that pen and paper solution wouldn't exist, whereas the numerical methods continue to work just fine. So in a sense, there's nothing special about this particular equation other than it's nonlinear. And it's also a very concrete equation that we're going to use several times through today's lecture. Keeping in mind, the methods we generate are going to be much more general, and simply by changing one line of code, we can solve a different problem. And I'll show you how to do that later in today's lecture. So I said I was going to introduce to you 2 methods. One's called the bisection method and one's called the secant method. And along the way, we'll introduce a 3rd method called Newton's method. Just want you to focus on the bisection method. Here's the setup. You can see on page 8 here that we've got a function, a portion of which is drawn in blue. Now, what we need to do in order to kick off the bisection method is identify a range of X values and in somewhere in that range, the function crosses the X-axis. So what we want is a function, and I'm going to assume that the function has this property called continuity. Now, for those of you that are studying analysis in mathematics, there's a very formal, rigorous mathematical definition of continuity. For an engineer, what continuity means is, can you draw the curve with a pen in your hand and draw it without lifting the pen and moving it and lifting it and placing it somewhere else? So if you can draw a curve with your pen, the function's continuous. They're the functions we're going to operate with to solve a problem, a algebraic, a nonlinear algebraic equation using the bisection or the secant method. So this function is continuous on this interval, which means you could draw a line from x low to x high and trace out the value of f along that curve without lifting your pen. But we need to kick it off, we need two values of x, and they need to be chosen in such a way that one is too low and one is too high. And what I mean by too low and too high is that for one of those values, the function value f is positive, and for the other value of x, the function value is negative. That means that the function value changes sign as we range from x low to x high. So you can sort of get the sense that if one of the values is too low and one of the values is too high, sort of like the Goldilocks zone, somewhere in the middle must be a value where the function crosses the horizontal axis. And the bisection method exploits that property. The bisection method says we absolutely need to kick off the bisection method with a value that's too low and one that's too high. We then divide the interval in two, and that's done by defining this value x mid, and x mid is the average of x low and x high. So it's x low plus x high on 2, just the average of them. So we divide the interval in two. Then we select the subinterval where the sign of f changes and repeats. Let me show you what that means. So get this picture in your head. Okay, so the function value it's positive at x low. The function goes down, it crosses the horizontal axis at some point, and then it gets to a value of x high where the value of the function value at that x high is negative. What's important is that the sign of f, whether it's positive or negative, it changes between the two values of x low, between x low and x high. Okay, we test the midpoint and we find that because f at the midpoint, that's this value in the middle dot, times the function value at x low, because both fx low and fx mid, because they're both positive, the product of those two values is a positive number. So there are no numbers floating around here. I'll show you a numerical example shortly. But the pattern is, because fx low and fx mid have the same sign, because they're both positive, we know that the function value isn't zero in that range. And so we can confidently say that wherever the function value changes sign, it can't be in this lower range, because both fx low and fx mid are positive. In other words, because fx mid times fx low is a positive number, the exact value of the number doesn't matter. What's important is that it's positive. Because there's no sign change in f here, the sign change must occur between these 2 points, fx mid and fx high, and x mid and x high. So we start with a function that looks like this, where we've constrained the range where the solution, the crossing point, must be squeezed between x low and x high. We test the function values at fx low, fx mid, and x high. If this condition here is satisfied, let me see if I can highlight it. If that condition is satisfied, we know that that the solution must exist in the upper subinterval. And so we update the value of x low to be equal to x mid. So notice if I switch backwards and forwards between these two equations, one thing that changes is X low is bumped up to the value of what X mid used to be. And so after one iteration of the bisection method, we've halved the width in which the solution must exist. We've squeezed it into the range, into this range, which is half as wide as it initially was. It was somewhere in this range between X low and X high. After one iteration, we've squeezed it, and we've got another problem. Now we've got a function which is positive at one end of the interval, negative at the other, and we can repeat. Alternatively, if this condition is satisfied, this is the opposite. So the one I'm about to highlight here, this is the opposite condition to the one that was satisfied on pages 8 and 9, on page 8, on page 9 rather. And then we select the lower subinterval. So this is the second alternative. If we start in this pattern, we know that if fx mid times fx low is negative, so here's x mid is a positive number, fx low is a negative number, and we know that a positive times a negative is a negative. So if this condition is satisfied, we can confidently rule out the upper subinterval as a place where the solution exists. It must exist somewhere in this lower half. So we go backwards and forwards between these two. We can rule out that half. We can rule out the solution can't exist in the upper subinterval. It must be in the lower subinterval. And we continue. We continue until we're close enough to the solution. There's different ways of deciding when to stop this algorithm, and it has to be stopped because otherwise it'll just keep on iterating forever. The solution, the iteration method that I've chosen here is that the absolute value of fx mid is less than some tolerance. So we keep going until the function value evaluated at what we think is the crossing point is really close to 0. Let's say 10 to the minus 6. So that's the bisection method. We take an interval and we progressively halve it up by moving the upper interval, the upper bound, the upper limit down and the lower limit up until we've squeezed the solution into such a small range that we've effectively found the solution. If we want it more accurate, we can reduce the tolerance here. So here's some Python code. I'll show it to you here. I'll point out the main points to you on this and the next slide, and then we're going to run it live. So here is our first code for solving a nonlinear equation using Python. You can see in lines 1 and 2, it's where we define the function f that we want to find the solution of. And so this expression here in line 2 is exactly the equation that occurred at the bottom of page 7. So the function is only a one-line function. It simply returns the value of the function at a specified value of L. We then have in lines 4, 5, and 6, we have in line 4, we have the tolerance value. This is the value that we set to a really small number, and we keep iterating until the function value at the midpoint of the bisection algorithm is less than that value in magnitude. X low and X high need to be initialized. These are the two values that we have to choose to be. One is too high and one is too low. We know the solution, the code assumes that the solution is somewhere between 6 and 10. And in this particular problem, if we'd plotted what the function looks like, remember the problem is to find the height L corresponding to volume 500. We know it's about 8. Certainly it's bigger than 6 because the volume at 6 is about 350. It's certainly less than 10 because the volume at 10 is about 700 or 650. So we're going to start the bisection method with looking for a value somewhere in the range 6 to 10. We could have chosen other values, but it's critical that we choose a value either side of the solution. We then prepare the bisection algorithm by computing the midpoint, which is the average, remember, of the x low and x high. And then the main iteration, the main loop, is in lines 10 through 16. Now you can see in lines 9 and 16, I keep a track of the number of iterations that the bisection method uses. That's not strictly necessary, but it's helpful to get a sense of how hard, how difficult, how computationally intensive it is to solve the problem. And then lines 11 through 15 are the Python code version of these two tests that were presented on pages 8 and 9. So it's something to do with fx mid times the product of fx mid and fx low. And here's the test. If fx mid times fx low is positive, then we bump up the lower limit. Otherwise, we bring down the upper limit. And so we've divided the interval into two, and we've either chosen the upper subinterval by bringing the lower limit up, or we've chosen the lower subinterval by bringing the upper limit down. Line 15 is critical. We compute the midpoint for the new interval, the one that's been halved, and we go again. That's the key part of the code. So let's run it live now. It is bisection. And so this code that you see, here in front of you is exactly the code that occurs, that it's in the lecture notes. It's also been posted on Blackboard, and it's also available in the lecture code channel on Discord. So you've got a way of running it yourself. So here we are. We've got in lines 1 and 2 we define the function. Lines 4 to 6 we initialize with the tolerance and the upper and lower limits of the solution, and in lines 8 through 16 we compute the solution, and we keep iterating around until such time as the absolute value of the function evaluated at the midpoint, until such time as it's less than or equal to this tolerance. I've called it EPS. Okay, let's give it a go. Let's run bisection. And what you see here is it's found a solution, 8.156600, It took 26 iterations, so it took 26 loops of half, until we squeezed the function value down to such a point that it was effectively, we found our solution. And the best part about it is that we can check our solution by substituting the value that we'd found, the solution, the numerical solution. We pop that back into the function and evaluate it down here in line 18 of the code. We can find the solution, we can put it back into the function value, and we see a small negative value here. That's pretty close to 0. If we wanted to get it even closer to 0, we could make the tolerance even smaller. Let's make it 10 to the minus 8. Let's run that code again. A couple of things you'll observe. This time it takes 33 iterations because we're going to insist on a higher level of accuracy of the solution. And sure enough, when you pop that solution that's been obtained with the finer tolerance, you see that to 1, 2, 3, 4, 5, 6, 7, 8 decimal places, we've found the point at which the function value f intersects the horizontal axis. So we're done. That's our first use of in this case, the bisection method for let me just break out of here. So I've captured here on slide 13 the summary of the results that you've just seen online there, with exactly the parameters, with the tolerance of 10 to the minus 6. It takes 26 iterations and we get the answer to within 1 part in a million. That's pretty handy. And keep in mind that that method, the only thing we'd need to do to change the function value or the nonlinear equation that was being solved, the only thing we'd have to do is redefine the function. And if I get time, I'll show you how to do that towards the end of the lecture. So we've got a comment in the questions lectures channel that said that looks like -0. The answer is what that means is if I displayed the value of the solution to a greater number of decimal places, you'd eventually see some 0.0000 something would turn up, and so it's a very slightly negative number rather than exactly 0. There's no such thing as effectively when we're solving problems like this. There's no exact solutions. We've given up on the exact solution. But I tell you what, if you're designing a bridge or an aeroplane or a rocket that lands on its tail, then answers to 1 part in a million, maybe 1 part in 1 part in a million, they're sufficiently accurate. Okay, so it comes back to that quote that I listed earlier in the lecture today, which is better to get an approximate answer to the right question than a so-called exact answer to the wrong question. So there's their first method, called the bisection method. Second one I want to introduce to you is something called the secant method. And you might ask, why would we look for a different method if the bisection method works? Well, it's always good to have multiple ways of solving the same problem. The secant method we'll see is actually, at least for this problem, it's actually faster. And I'll show you that live later this morning. So with the secant method, we also start with 2 points. And I've indicated them here as red dots. Keep in mind the solution that we're looking for is the value of x where the blue line intersects the horizontal axis. So we're looking for what we're calling the solution is the x value where the blue line intersects the horizontal axis. And we start with 2 guesses. And we're going to start with 2 red dots, the 2 points represented by red dots. Unlike the bisection method, we can start the secant method with 2 x values. They don't even have to be on opposite sides of the solution. They've just got to be 2 different values of x. And as long as the function value f is well behaved, talk about that later, then the secant method would also work. So we start with 2 points and we represent them by their coordinates in the plane where we've got x0 and the function value at x. There should be a little tick mark here on the vertical axis to show that this fx0 is the ... It's the function evaluation at the x value of equal to x0. And likewise, this red dot, its vertical placement is the function value evaluated at x1. There's nothing special about x1 and x0. We can choose them almost arbitrarily. They don't have to be either side of the solution. So what the secant method does, it starts by drawing a straight line between those 2 red dots. That red line is what's known as a secant. It's a line which connects 2 points that are on the function of interest with a straight line. So again, the function, the solution we're looking for is the point at which the blue line intersects the x-axis. And we start by constructing a secant, which is the line that connects those 2 red dots. And notice if we extend that straight line, eventually that's the red straight line will intersect the x-axis. The point at which the red straight line intersects the x-axis we'll call x2. Okay, so we started with x0 and x1, chose them almost arbitrarily. We drew a straight line through those 2 points. The intersection of that straight line we called x2. And then we've got 2 new values we can work with. We ditch x0, throw it away, and then we use the secant method, starting with x1 and x2. Remember, x2 was defined as the point at which the red straight line, the secant, intersected the x-axis. At that point, we've got x1 and x2. We've also got x0, but we throw x0 away. And we've got 2 new points, x1 and x2. We draw a straight line through those 2 points. A new secant. It's this little red line. It really extends forever. We don't need to extend it forever on the figure because the only point we're interested in is the point at which the red line intersects the x-axis, and we call that F3. And so there's this leapfrogging that goes on where if you've given x0 and x1, you can define x2. Given x1 and x2, new secant, new intersect, define x3. At this point, you could throw away x1. You've got points x2 and x3. Draw a straight line through them, and you can see in this diagram, it's really just it's something I drew rather than computed, but you can see how quickly the intersection point of these secants converges to what looks like it's converging to the point at which the blue curve intersects the x-axis. A little bit of mathematics here. I don't expect you to be able to derive it. I wouldn't expect you to be able to derive it under exam conditions, for example, but I want to present it to you because we're engineers, we need to understand the tools that we're using. And so I'm giving you enough here that you can rederive the equations that exist in the code using the equations on this slide. So again, this is not a course about mathematics. It's a course about using maths where it's appropriate to set up code that we can then run and solve problems of engineering interest. So the equation of the straight line connecting the points x0, f of x0 and x1, f of x1, that's the equation of the straight line between these 2 red dots. If that red straight line has this equation, y equals this expression times x minus x1 plus f of x1. Takes about half a page of algebra, but it's not hard in itself. Do I expect you to be able to derive it for this course? No. Is there anything here beyond high school arithmetic? No. I want to be clear, absolutely clear about where I'm getting these equations from, so I'm presenting the equations for you here. Now, this equation, the top equation that you see here, y equals ... it's the equation of the red straight line, the secant between these 2 red dots. If we then set y, the vertical value equal to 0, we get this x2. Remember, we defined x2 as the x value corresponding to where the secant intersected the x-axis, namely where the vertical value was equal to 0. If we then rearrange, we get an expression for x2 that looks like this. Let's just pause at this point. Look at the right-hand side of that equation. We've got x2 is equal to stuff. Let's look at what's on the right-hand side. x1, we know what x1 was. We started with x1. We assumed that was one of our 2 points. Good, we know x1. We also know the function value at x1 because we can simply call our code and evaluate the function at that point x1. Good, so we know that term. We know x1, we know f of x1. then we've got this ratio of differences. We know what x1 is, tick. We know what x0 is. Remember, we started with x0. And we know the function evaluated at both x0 and x1. So what this equation says is that if we know x0 and x1, we can compute the expression on the right-hand side and calculate x2. Remember, x2 was the point at which the secant, the line through these two red dots, intersected the x-axis. So I don't expect you to be able to look at that equation at the bottom of in the middle of the screen there and immediately make sense of it. That might take a little bit of time. But I do ask you to observe that if you know what x0 and x1 are, you can compute x2. Good. So that means that if we know what x0 and x1 is, we can compute this intersection point. We then throw x0 away and we compute x3 based on knowledge of x1 and x2. Well, the equation for computing x3 depends on f2, x2, and x1 and the functions evaluated at those 2 points. And then we can define f4 as the secant connecting the points x2 and x3, the intersection point, and so on, dot, 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 dot. So this sequence of function evaluations is iterative because each step relies on calculations done in the previous step. We can leapfrog along from knowledge of x0 and x1 to compute x2. With x1 and x2, we can compute x3. With x3 and x2, we can compute x4, and on we go. They're the equations that are captured by the code in the secant method. And here's the code itself. You'll see it looks remarkably similar to the bisection code that we saw a few slides ago. Again, code posted in the lecture code channel and also on Blackboard. Lines 1 and 2, we define the function that we're trying to solve. Lines 4 through 7, we set up our initialization, the tolerance, our initial 2 guesses, in this case 6 and 10, and prepare to count iterations. And then all the work for the secant method iteration is done in lines 8 through to 14 of this code. And then in the final 3 lines, we simply display the results. And you can see in line 11, it computes the intersection point. So the equation that I'm highlighting here in line 11 is exactly the equation that occurs in the middle here, the x2 value, x1 minus f of x1 times a ratio of 2 differences. It's exactly that equation there that you see in line 11. So this is computing the secant intersection with the x-axis. Now the iterative loop here says that if we know the 2 most recent values of x, we can get an updated value of x. We then throw the oldest value away and work with the most recent pair of x values. It's like we started with 2 red dots. We do a straight line, computed the intersection, computed threw the oldest value away, started with 2 new x values, drew the straight line, intersection, throw the oldest one away, and continue. And so this code is subtly different from the equations that you see on page 17. And the reason for that is we don't actually store the whole sequence of x values. All we need to do is store the 2 most recent values of x. The 2 most recent values being the x values corresponding to the dots. We started with 2 dots, straight line, intercept, compute a new value of x, throw the old value of x away, we've got 2 new red dots again. So it's like this, we walk along taking only the 2 most recent value of x because they're enough to define the straight line, new intercept, and away we go. And so this code here enables us to get away from actually storing X1, X2, X3, X4, X5. You could do it if you like, but the code would be more complicated than the implementation I have here. And we keep going while ever the same condition satisfied before, while ever the function value evaluated at the most recent value of X, the most recent intercept, is greater than some small tolerance. So here's the code. Let's run it live. Here it is, exactly the same code. Is it? No, it's not. It's the wrong one. This one. There we go. So this is the exact code I just presented for you on the lecture slide. Here it is. Define the function in the first two lines, tolerance, initial values, iteration counter, and all the action happens in lines 8 through 14 in this while loop. Classic example of the use of iteration in the form of a while loop. We want to continue doing some calculations until a particular condition is satisfied. So while ever it happens that the function value is too big, is too far away from zero, we keep computing. Pair of straight lines, intercept, update the new value of X, throw the oldest value away, and repeat the same calculations. It's the same equation in line 11 that gets executed, but with an updated value of X. So let's run it. And here we go. What you observe is the same answer, at least to about 6 decimal places, 8.1566. Notice how few iterations are needed. In this case, it's only 4. In general, the secant method is a faster way of solving problems than the bisection method, which is nice to know. Now, in this case, I'll show you in 10 minutes or so how to actually time the amount of time it takes to compute that those solutions. But in this case, it's interesting that I think it was 26 iterations of the bisection method. Same answer in the secant method only needs 4 iterations. Let's see what happens if we decrease the tolerance to 1 part in 100 million. In general, what would you expect to see? There'll be 2 observable effects if we decrease the tolerance here. What would you expect to see? So if we run it, let's run it, and let's see if we can. Okay, so we took an extra iteration. That's one observable fact. It's not surprising that requiring a solution to a greater level of accuracy requires an increased number of iterations. The other observable fact is that if we substitute the answer we get back into the function value itself, so that's done in the code by taking the solution that we obtained, the most recent iterate, pop it into the function value, evaluate it, the function at that value of X, we get a value that's very slightly negative. It looks a bit odd to see a number of minus 0.000 written. It looks like it's saying -0. That's not true. What would happen if we displayed this answer out to 10 decimal places instead of it's a pretty accurate answer, isn't it? Let's do it again. Wow. There we go. So the secant method is really powerful. We get an expression that's correct to within 1 part in 10 to the minus 8 with just one extra iteration. It's a really powerful way of zooming in to find the solution there. So this is a really accurate solution. Sure enough, you can see it's a slightly negative number. For all practical purposes as an engineer, we have found the solution. It's correct to 8 decimal places. More accuracy than is needed in engineering applications. Now let's just bump that back down to how it was, and we're good. Okay, so there we've got, to summarize for you on slide 19, summarize where we got to with those simulations. I guess the most subtle point was the one I discussed when we looked at the code. It might look a bit odd that the solution here is coded only in terms of x0 and x1, when the method looks like it involves also x2, x3, x4. Better to think of x0 and x1 as the 2 most recent values of x, rather than the initial values that they start off here in lines 5 and 6, because x0 and x1 will both be updated. You can see them here being updated in lines 12 and 13. And so when this code finishes, x0 and x1 are not their initial values here. They've been updated. So that's the most subtle point of this code implementation. And this often happens in when you're writing code to solve engineering problems. We understand the problem in a particular mathematical way, but when it comes to implementing that code, it sometimes makes sense to switch our notation for efficiency purposes. And I would argue that this is pretty efficient, because we don't need to store x2, x3, x4, x5, and x6 and so on. We just need to store the 2 most recent values. And once we've found what x5 and x6 are, what the initial values of x0 and x1 were, irrelevant. Okay, so I said we were going to look at 2 methods. Bisection method, squeezing the interval down by half. Secant method, drawing lines between pairs of dots, calculating the intercept point. There's a third method that's known as Newton's method. And we're not going to, unlike bisection and secant method, we're not going to present the code. The reason for it is it requires some use of mathematics that not all students in the class have. But I can really easily illustrate how the idea behind Newton's method. Newton, by the way, is Isaac Newton, Sir Isaac Newton, probably the greatest scientist that has ever lived. His name's associated with this algorithm. He first arrived it in the 1600s. So Newton's method says this: we start with an initial estimate x0, indicated here as the x value out on the right hand side, about 1,000. And then what Newton's method says is that we create a tangent line to the function. And so the tangent line is this red line here that just grazes the function value. The function we're trying to obtain the solution to is the blue curve. Newton's method says we choose an initial estimate and compute the tangent line that just grazes the function through the point defined by x0. Now, computing this tangent line requires mathematics in the form of calculus. For those of you that have studied calculus at high school, it involves the computation of derivatives. So computing the tangent line needs calculus. It needs an expression, not just for the function f, but its derivative. Now, if what I've just said to you in the last couple of minutes doesn't make sense because you haven't studied calculus yet, then don't worry, because we're not going to implement Newton's method in this course. I just want to give you a visualization of how Newton's method works. So Newton's method starts with initial iteration, initial guess, x0, computes a tangent line that just grazes the function, and then we extend the tangent line as a straight line down until it intersects the x-axis. We call that point x1. And x1 is an improved estimate of the solution. What do? It's an iterative method. So we dot, and compute the tangent line, the straight line that just grazes the function. They've got the same gradient at the point x1. This straight line here, this little red line segment, and the blue curve are tangent at the point x1 because they have the same gradient at that point. Define a straight line which starts at the grazing point and extends down to the x-axis. Call that x2, and so on. It's no coincidence that Newton's method and the Secant method look really similar. They are actually connected in a fairly subtle way, but also a sort of obvious way. You're sort of drawing these tangent lines or secants as the two values in the Secant method approach each other. The secant increasingly approximates the tangent line. So Newton's method is also known as the Newton's-Raphson method. It's much more popular than the bisection or secant methods. So Newton's method is a workhorse of solving engineering problems. It gets extended in all sorts of ways to solving problems that have more than one x variable that might have 10, 20, thousands, millions of x, well, maybe millions, hundreds of thousands of x values. They're extensions of Newton's method. So Newton's method, if you go on and study numerical analysis or apply solution methods that are presented in second and third year engineering courses, you will use Newton's method, I can guarantee it. For the purposes of this course, just the first course in computing, we can't assume knowledge of calculus for all students that are in this course. Some of you are taking Math 1110 this year, some of you won't take it until next year. But the calculation of these tangent lines that define Newton's method requires these derivatives. Because it's beyond assumed knowledge for this course, we won't consider Newton's method in this course. On the very last slide of today's lecture, I've given you some links where you can follow up the details in the textbook. Textbook does a really nice treatment of Newton's method coupled with Python. It's very powerful. And so if you're interested, if you're studying calculus, if you've studied calculus, Newton's method is absolutely within your scope. I'd highly recommend the link that I give you on the last slide of today's lecture, because the textbook treatment is really very good. And the final dot point there is that you can think of the Secant method as an approximation to Newton's method. The difficulty with Newton's method is that it needs the knowledge of what's called the derivative of the function. So in fact, Newton's method needs two functions. It needs the function we start with, the one we're trying to find the solutions of, and it requires the derivative of that function. Now, for simple problems like the one we're working with in this, the volume and the truncated cone, finding the derivative is very straightforward if you know a little bit of calculus. For more complicated values of f, for more complicated forms of f, computing the derivative is really hard, or can be really hard. So there are approximate methods, and they effectively amount to the Secant method. So bisection is really simple, but it's a bit time consuming. Newton's method is really fast and powerful, but it requires knowledge of the derivative. And the Secant method somewhere in between. It only requires the function, not its derivative, but it's also faster than the bisection method. So altogether, those three methods, bisection, secant, and Newton's method, all of them solve these, are able to solve non-linear problems, but only secant and bisection method are considered in this course. Couple of extensions, and so we're going to take the code we've written, and just reframe it a little bit. And I'll show you how to time code as well. I want you to look at this code that you see on the screen here on page 22. You'll see that the bulk of it, I'll highlight the code in lines 5 through to 13. You've seen those lines before. They are the bisection method that we presented on an earlier slide. The difference with the code that we've previously seen to the code that's on the screen here now is that the code that's on the screen implements the bisection method as a function. So here we have the function definition on line 4. The bisection method needs 4 things in order to do its job. It needs the function value we're trying to solve, the function we're trying to solve. It needs initial estimates, low and high. Remember, for bisection, they've got to be either side of the real solution, and a tolerance. I called the tolerance EPS before, but it's the different name for the same quantity. So the bisection method written as a function looks like this. It takes in the function value, estimates of the low and high values for the solution, and a tolerance, takes them in as input parameters. It does its thing, and then it returns the estimate of the solution, plus also the count of the number of iterations. And the nice thing about wrapping all that functionality up in a function is that we can call, as in line 16 here, we can actually get the bisection algorithm to do its job in a single line of code. We hide away the details. Sarah talked about this last week. Hide away the details in a function. Once we've written and tested this bisection code, we don't really care about the details. What we want to be able to do is use it to solve engineering problems. And here it is. Here's the call to bisection. I've called it my bisection. We pass in a function value, defined here in lines 1 and 2. We pass in the low and high values for X, for the values either side of the solution. They're not particularly critical. We'll change them in a moment and see what the impact is. And then we pass in a tolerance. And then at the bottom of the screen, you'll see the solution, the number of iterations, and a check that the value is in fact a solution. And again, it's the code here is called bisection function, bisection_fn.py. I posted the code in Blackboard. It's in the lecture code channel. So let's run it now. Bisection function. Here it is. Let's just check. It's the same code. We define the function. We define 2 functions. One is the function we're trying to find the solutions of, or solution of. In lines 4 through 14, we define the bisection code itself. All the work you've seen before. I won't go over those details. It's exactly the code you saw before, just wrapped up inside a function. 4 input parameters, function, estimates, tolerance, and then we return the function estimate plus also the number of counts, the number of iterations. So let's run this code now. Run, what's it called? Bisection function. Exactly the same results as before, no surprise. Okay, why? Because we passed in the same initial values and the same tolerance. Let's run the code again, this time changing the tolerance to 10 to the minus 8. Takes 33 iterations now. What happens, this line here, line 16 is the only line of code we need to modify to experiment with the bisection method. What happens if we start the bisection method with the same tolerance as before, but with a different lower limit, 4. Run it again. 25 iterations. We know the answer's right. We can substitute back into F and get the answer. What happens if we bump up the initial? So we suppose we only know the answer somewhere between 4 and 12. Run the code again, 27 iterations. I really like this solution approach, because what it means is once we've written the code to implement the algorithm, we can wrap it up in a function, put the function somewhere else in our code, and not worry about it. We can just call it as we need. And that's a really good technique for solving engineering problems. Break a big problem down into small chunks, solve them, put them in functions, hide the functions away, and get back to solving the problem of interest. So there's the bisection function written, the bisection algorithm written as a function. Got a little bit of commentary there just for your reference. I've talked about all those things. We can do the same thing with the secant method as a function. Same idea. Function, I've written it in a slightly different form there. That's unintentional, was it? Doesn't matter, same function, it's all good. I've just realized it's not a bug in the code. It's an alternative definition of the same function written in a slightly different way. Okay, so then we've got the secant algorithm written as a function. Again, all the details in lines 5 through to 10 you've seen before. They are exactly the same equations as before. They've just wrapped up inside a function called mySecant. So let's run that one now. It won't take us long. Here is the secant algorithm written as a function to be optimized, or the function to be solved. The secant function written as a function takes 4 input parameters and returns a number of iterations as well as the current estimate. So let's run that now. And we see 4 iterations, and we've got the solution right to about 6 decimal places. Again, if we want to bump the fiddle around, experiment with the tolerance and the limits, run it again, and we find it takes more iterations, and we've got the solution accurate to within 1 part in 100 million. So that's really good. So what have we done so far? We've introduced 2 methods for solving nonlinear equations: bisection method, secant method. We've written them both as standalone programs and as functions. And that's actually a pretty common coding strategy. Write the function, solve the problem. Once you've solved the problem, wrap it up into a function, hide the details of that function away, and that makes solving the overall problem easier by taking away the distraction of the details that are buried inside the function. So we're looking at extensions now. We looked at the extension of writing the 2 methods as functions. The next extension I want to show you is how to time code in Python. That means calculate or return the number of seconds or minutes and sometimes hours or days that it takes to perform calculations. And it's really easy in Python. Number of ways of doing it. I'm going to show you what I think is pretty much the simplest way of doing it. And I'd recommend that you use this too in cases where you want to time code. And I'm doing it here because what we're aiming to do in the last couple of slides is make a timing comparison between the secant method and the bisection algorithm. So in order to time code in Python, we need a line in our code that we import from the time module. That gives us access to the functions that are inside this externally defined module called time. The time module has a range of functions. The only one of interest to us at the moment is the one called perf underscore counter. It's short for performance counter. And because it's a function that's available inside the time module, it's accessed by writing time dot and then the function name inside. It doesn't actually need any arguments, so we don't need to call it with any arguments. We've just got this empty parentheses that we call it with. And what time.perf counter does is return the value of a clock. It actually returns a float number in seconds. The Python language doesn't define what that clock was relative to. And in fact, that doesn't matter, because the only thing that matters for us when we're timing code is the difference between two successive times on a clock. So if you're trying to time how long it takes you to swim 50 meters, it doesn't actually matter that it's 10:30 in the morning. What that matters is that it's 10:30 in the morning when you start, and it's 10:31 when you get to the other end of the pool. So it's taking you a minute. That's what the perf counter function does. It returns a value of a clock, and then what you do is compute the difference between two successive calls. And the classic way that you time code is shown in the 4 lines of code that you see at the bottom of the screen here. The 4 lines. The first thing you do is you compute a start time by calling the perf counter function in the time module, and you store that clock time in a variable, in this case called tstart. Then you do some calculations. In this case, we're going to call the bisection algorithm, or the bisection function, wrapped up in the code that we've seen on the previous slides. The values of xb and numIntB don't matter here for this illustration. And then as soon as we've done that calculation, we call perf counter again and store the stop time in this variable called tstop. So the amount of time it took to run the code by bisection is the difference between the stop value and the start value. And that's it. T_bisect is then a value in seconds of how long it took to run this code. So let's do it. I'm going to run some code here. The code itself is too long to show you in the slides, but again, I've posted on Blackboard and it's available in the lecture code channel. So we're going to run this code called bisection versus secant.py. It's the last code we run for today's lecture. So here's the code. It's about 50 lines long. Don't be worried about the length. Let me show you the key points. We import the time function because we're going to do some code timing. We then define the function of interest that we want to find the solution to. We then define the my bisection and my secant algorithms. These are exactly the code that you've seen on previous slides. So we're 25 lines in, and all the code we've seen before. Here's where the action happens. Remember, what we're going to try and do is we want to do a comparison here of the time it takes to run both the bisection algorithm and the secant algorithm, finding the solution for the same function f using the same parameters, initial low and high estimates with the tolerance. And here's the 4 lines of code using the pattern that you just saw on the slide. If we want to take how long it takes to run the bisection algorithm, we calculate what the start time is. We run the algorithm in the form of a call to the my bisection function. Then we call the performance counter again, and we look at the difference between the start and stop time. And we call that T_bisect because it's time to run the bisection algorithm. The next 4 lines of code are exactly the same format. The only difference between these 4 lines of code and these 4 lines of code is that on line 33, we call my secant rather than on line 28, computing my bisection. Same parameters, same start time counter, stop counter, and compute the difference in the 2 times. And then the rest of it is just displaying results. So let me show you what the results look like before we look at that code again. So here you see we've run the code and we see that a couple of things, both the bisection algorithm and the secant algorithm have computed the same solution, or at least they're the same to about 6 decimal places. That's encouraging. For each of them, we substitute the function value obtained back into the solution value obtained back into the function, and we get something that's pretty close to 0. However, the bisection algorithm took about 7.5, about 7 times 10 to the minus 5 seconds, so about 70 microseconds. 70 microseconds. Whereas the secant algorithm took about 1.7 of the same unit. So we ran this code, and the secant method was about 3.9 times as fast as the bisection method. And I've done that. I've computed this ratio 3.9 simply as the ratio of the run times here, noting that the secant method is faster. Does it really matter if a program takes 70 microseconds or 17 microseconds? Probably not. You're not going to discern any difference on a human scale by running both these algorithms. However, for larger problems, for larger data sets, so where you might need to run the same solution on thousands, tens of thousands, millions or more times, it really makes a difference. I've worked with Brenton in recent times on problems that might take a day to run. The difference between a method that runs 4 times as fast as the original algorithm might mean that you could that what you could do in 24 hours using one method, you could solve in 6 hours with another. That's a big difference. Newton's method on this problem would be faster again, but we're not going to code it. Let's see what happens if we run this same code again. We get the same results as before, but the secant method this time is 4.9 times as fast, whereas before it was about 3-point-something times as fast. Let's run it again. This time it's 4.8. This time it's 4.8, 5.2, 5, 4.8, 5.2, 4.7. Why is the code taking different amounts of time to run? Why is the secant method always as a fixed number of times as fast as the bisection algorithm when it's called with exactly the same parameters? How can that be? The reason is that my computer, and I'm just running this on my desktop computer here, my computer's doing other tasks, and the time that the Python environment is able to access to perform computations fluctuates, depends on other tasks that I'm doing. If I was to run a particularly numerically intensive task elsewhere on my computer, the algorithm would run a different number of times as fast. So that's something to keep in mind. With large programs, it's often difficult to exactly calculate how much faster an algorithm is than another one. But it's worth keeping in mind that as a general rule, the secant method is almost always going to be faster than bisection, and Newton is going to be faster than the secant again. So there we are. I've got the summarized there, and that's a summary of the results we've seen. Although we've seen that the run times actually depend on particular instances of the run, rather than and they're not something that can be fixed in advance. So in summary, I've introduced what it means to solve nonlinear algebraic equations, and we've introduced these 2 methods, bisection and secant. I've given you the code for those. I've also introduced a little bit of mathematics to justify each one. The point of this course is not to understand or not necessarily to derive the mathematics for both, but I do expect you to be able to use both these algorithms. And I've given you the code for doing it. What you need to do and what you'll need to do in subsequent weeks' activities in the lab, for example, is to use the bisection and secant methods for solving problems, different forms of problem, and modify the code. And we've seen some number of extensions, writing the solution methods as functions and also timing of the code. If you want some more information, Newton's method in the textbook is the treatment is particularly good in terms of implementation in Python. I've included here in more information because it is beyond the immediate scope of this course. If you've studied a bit of calculus before, if you're really on top of the content in this lecture and you want to extend your knowledge, I'd highly recommend section 7.2 of the text. If you haven't studied calculus before, just put a mental note in that you can return to this content once you've studied a little bit of calculus, such as in, for example, Math 1110. The treatment in the textbook of the bisection and secant methods is a little bit different to the one I've followed here. They're both very good treatments in section 7.3 and 7.4. They're also a little bit more complicated than the ones I've presented here in today's lecture. And they're more complicated because they set about restructuring the code in such a way that it minimizes the number of function evaluations. As problems get bigger and the nonlinear problems, the nonlinear functions get more complicated, almost all of the computation effort in either the bisection or the secant methods, almost all the computation goes into function evaluations, evaluating f for a particular value of x. The code that's presented in the textbook for bisection and secant methods is structured in such a way that the number of function evaluations is minimized. So it's actually possible to get both the bisection method and the secant method to run faster than the code I presented here by using the code that's presented in the textbook. I would only recommend following the code in the textbook once you've fully got your head around the implementations we've seen in today's lecture. It's really elegant code, although it's written in such a way to optimize speed at the expense of intelligibility, at the expense of being able to easily interpret what's actually going on in the algorithms. And I promised earlier that there was for those of you that are interested in coming up with or deriving or seeing how the derivation of the functions in order to compute the volume of the truncated cone, there's a link here. I won't say it's beyond the scope of the course because it uses calculus. We've been able to very successfully implement these functions here today without needing to know where the particular nonlinear functions come from, but there's a link there should you want one. Wonderful. So thank you. That's the end of today's lecture content. We'll next meet on Thursday, and until such time, I'll see you later. Thank you. Bye.